I didn't give you this spiel I gave it to the other class. We can talk very generally about polyatomic vibrations, and we're going to learn that molecules that vibrate that have more than two atoms, they don't really vibrate all that much differently than a molecule that has two atoms. The theory is basically the same, it's just more complicated, more bonds, more ways to move. So we're going to have to come up with a clever way to represent the vibrations of all these bonds in a way that satisfies something that looks like a harmonic oscillator. Right? We're going to have to try to figure out a way to think about the motions of all of the atoms in a molecule in a way that gives us harmonic oscillators. And there's a really logical procedure to do that. And unfortunately, the mathematics for it are even beyond me. Like, I still don't fully understand how to calculate these things. But I can talk to you about it qualitatively. And then what we're going to see is that the theory for a polyatomic molecule basically just simplifies. So the same theory we saw for a diatomic, the energies are h nu, v plus 1/2. See all of the same things. Except now a bigger molecule has many harmonic oscillators. It's a combination of many that each represent a different motion. We kind of know this from infrared spectroscopy. You got the idea of a stretch in a bend, a rock, a scissor, and there's all these different vibrations. Each one of these is a unique harmonic oscillator that we represent the molecule with. Right? The molecule is consistent of some number of harmonic oscillators that we can represent it as, and we can derive exactly how many that is. Pretty easy to do that. So let's do that today. So the first thing we're going to think about is how a molecule in 3 dimensions. And we want to try to figure out how many different ways there are to vibrate this molecule, unique ways. So it's not a particularly hard argument to make. Let's just work it out nice and slowly. So big question today. How many unique vibrations does a molecule of N atoms have? Very simple question. How many vibrations are there? Unique ways to vibrate bonds. We'll be able to come up with a very, very specific number that's a function of N. Really great equation. Something that we'll never forget. It's one of those things that's buried in the back of my head and burned in my skull for the rest of your life. So let's make an argument about that. So let's come up with a molecule. All right. It doesn't matter what it is, but let's just think we have some. Right. So let's just a schematic molecule, we'll say. Not a real molecule, but the idea is that we have some atoms and they're attached to each other through springs. Maybe I'll color some to show that they're different atoms. Maybe we have some number of atoms that are all connected. Right? And they're all connected with springs. Right? And we can, in some sense, we can take each one of these bonds and say, well, each pair of atoms, in some sense, think of those individual diatoms. So one thing that we could certainly do is say, hey, what if I split the molecule up like this? What if I say, hey, I've got a harmonic oscillator here, and then I've got one here. Right? I just identify all my pairs of harmonic oscillator or atoms, my little diatomics, and so on and so forth. These are my diatomic-like pairs. And so you logically think, okay, well, let's just take this system, right? We have pairs of atoms that are connected by springs or covalent bonds or whatever they are. Let's just identify each one separately and analyze their vibration. But there's a problem, right? And the big problem with this statement, there's a couple of them, but the first one that's really obvious is imagine I stretch this one. Okay, so I stretch, maybe the people on Zoom can't see what I'm talking about, but let's say, for instance, I stretch this bond first, So it stretches, right? And then let's say I want to stretch this one next. Right, so let's say I stretch that one first and then I stretch this one second. The question we have to ask is, are these motions independent of each other? In some sense, does the potential of stretch 2, is it dependent on the position of stretch 1? Right, because what's happening? So as I do the first stretch, let me label the atoms. We'll call this one A, this one B, and this one C. Right, as I stretch AB, I change the behavior, the electronic behavior structure around atom B. Right, as I move B away from A affects B less. And just think about a Morse potential. We're stretching A and B. B's moving away. We're breaking some of that covalency, a very, very small amount. And then what I want to do is stretch B and C, right? But the stiffness of the bond between B and C in some sense depends on the stiffness of the bond of A and B. Because they share an atom together. So as you stretch A and B apart, you're changing the environment around B. And so then when you stretch C away from B, it experiences in some sense a different B than it would have if it never stretched away from A. Right? So remember, write that here. As I stretch BC, the behavior of the bond of the stretch is determined by the behavior of the connecting atom B, which is dependent on AB, the stretch AB. So as I change one bond, it affects the other one. I don't know how much it affects it. I could certainly assume that they're completely unrelated to each other. Okay, that's a perfectly reasonable assumption for me to make. But you find out very quickly that it doesn't work. Right? In the sense that you would say, okay, well, they might be all separate, but again, think of that atom being in the center, right? Imagine this is AB is a double bond, right? And BC is a single bond. As you move B away from A, you lose some of that covalence. You're changing the electronic structure of B. And so that means, therefore, C sees a different B depending on its position relative to A. Right? So in some sense, all of the atoms are correlated to each other. Right? So in this approach, right, you could just kind of logically extend this, right? It just kind of propagates through the molecule. Every atom is dependent on every other one. Every bond's vibration depends on the others locally. Now, I could change B and C, and then think about this bond way up in the far top, the blue one. You can make an assumption that, well, they're fairly far apart, so they probably don't affect each other. And that's generally true. There's some kind of locality. But in the case of A, B, and C, then you have an atom in conjunction, and very much as you change the AB bond, you're going to change the C bond. So that's a really bad way to approach the problem. Because now what we have to do is track everything independently on each other. The bonds in some sense aren't independent, right? They're all coupled. The vibrations are coupled. Right? I wish I had a nice experiment to show you this. But if you put a bunch of balls on a bunch of springs that are all attached like this, you can see that when you move, stretch B, when you stretch C, away from B and let go, it causes AB to vibrate. Right, and that vibration between AB propagates to A, the yellow atom, or A to the white atom, right? Everything propagates through the whole system as you stretch C away from B. So in order to think about the BC stretch and how it works, we need to think about all the other stretches. So a really bad way to do things. A really bad way to do things. It's a very complicated set of data. So we need to think of a different way to decompose these bonds and their vibrations into sets of vibrations that aren't coupled. In the sense that we can move atoms, groups of atoms independently, and those motions don't affect the other atoms that aren't moving. Right? We have a set of uncoupled independent motions. So what we want to do is identify. So the goal is identify a collective vibration of all the atoms that is independent and uncoupled to all other collective vibrations. Right? We're going to look at ways to move all of the atoms at once in unique ways that you can basically say that they're like individual bonds, right? They're these collective motions of the atoms, oscillations of a drum, that all interact independently. So how do we do that? So again, let's go back to our molecule, right? So I'm just going to draw another one. Something like that, right? Right, let's define, just like we did before with the diatomic, let's define a center of mass for the system. So in this case, I don't know where the center of mass is. I don't know where the masses are. Let's just say the center of mass is right here. So we're at the center of mass. Okay. And then what we're going to think about are the motions of each atom individually. So each atom is free to move in any direction it wants. So let me just label them, right? So we'll say 1, 2, 3, 4, and 5. Right, and each atom has a vector. We'll call it R. Sorry, that's not how I want to do it. Each atom has a vector originating from the center of mass, called its displacement vector. Right, it's just a vector that points to each of the atoms. And so on and so forth. Right, so we have these vectors that are pointing to all the atoms. Right, and each vector is a three-dimensional vector. It's got 3 components. This is 3D space. So displacement vectors R sub I are just vectors in XYZ space. Right, so each atom, therefore each atom has 3 independent coordinates. Right, so the whole problem, so the molecular motion, if you will, is 3n dimensional. Okay, so if we have 5 atoms, there are 15 different variables. Move all the atoms, right? Each gets twice. All right, so now, so there are 3n different, in some sense, there are 3n different ways to independently move all the atoms. However, there are a set of special motions of all the atoms that we call different names than just motion. We have some special collective motions. What are those special collective motions?
So there are some special motions, special dimensions, motional dimensions. Right, and it's really easy to think about what these are if we just kind of draw it. Right, there is a set of displacements, if you will, where all of the atoms move together. Right, so the idea is you have a motion of the center of mass. Right, the center of mass itself can move z, x, or y. Right, and if I move the system so that the center of mass is translating, sorry, that go away. Okay. So if I move the center of mass of the molecule, all the atoms are relatively with respect to each other at the same place. It's this whole molecule is moving as I move the center of mass. Right? If I can grab this, right, all the atoms are fixed relative to it, so I can move the center of mass, and all of the atoms move collectively, and none of their bonds change. And I'm not moving the atoms relative to each other. I'm moving them all collectively in one direction. Right? This is just translation. Right? So center of mass motion has 3 dimensions. And result in no vibrations or structural change. Right, so of these 3 n coordinates, the system has 3 n coordinates, 3 of them correspond to all just the center of mass moving. Up, down, left, and right, the atoms are not moving. They're not just moving the whole molecule by itself, just placing it here. Right, that's not a vibration. Right, so some of the motions, 3 of the motions in particular out of the 3n, are just translation. So that means, therefore, there are 3n minus 3 independent motional degrees of freedom. Or let me say dimensions. I've been using the word dimensions. Right, but there's another set of collective coordinates that also lead to no change in the structure. And that's if I hold the center of mass here and I rotate. If I just take the whole system and rotate. Right? So now I'm just changing the orientation of the system. Go ahead and start a new label. Let me copy this over. Right, so there are also 3 new ones. There's other 3 ones that also don't involve a vibration. Right? And those 3 are rotations about the angle, or around the axes. So there are 3 rotations that are collective. About the center of mass. And these evoke no structural change. No vibrations. Right? We're just moving everything. We're just changing our perspective. Right? That's all we're doing. Just changing our perspective. So therefore, when you include these now, there are 3n minus 6. Not G, but 6. Independent motional dimensions. All right, so just by counting, when we have n atoms, we have 3n different ways to manipulate the molecule. 3 of those 3n are translations of the whole system. And there's another 3 if it's a 3-dimensional molecule of the 3 different types of rotations. Rotate around the z-axis, the x-axis, and the y-axis. All right, so that means by definition, if there are other ways to collectively move the atoms, they correspond to displacements of different atoms with respect to each other. So that means that the remaining 3n minus 6 remaining degrees of freedom. And these are the vibrations. Okay, so we have a very, very simple rule. If a molecule of n atoms is 3D, then it has 3n minus 6 unique vibrations. And if it's linear, like a diatomic, then there's only 2 degrees of rotational freedom, then it has 3n minus 5. Okay. Most molecules have 3n minus 6. Right? Very, very simple argument, right? We fix the idea is we have a center of mass, it's fixed at the origin, right? It doesn't move. Right? We don't want the center of mass to move, we want it to be constant. There are 3 different ways to move the atoms with respect to the center of mass. 3 of them are translations, 3 of them are rotations. So 3n minus 6 must be vibrations. The only other ways to move the atoms, like there has to be these displacements of individual atoms with respect to each other, which are the vibrations. This rule is hard. Right? This is just pure geometry. And so this is just a general rule that if you have n atoms, you have 3n minus 6 unique vibrations. Okay? We don't know what those vibrations look like. Let's don't know what their energy levels are or anything like that. We just know there are 3n minus 6. So let's do some examples. There's just some very basic calculations. I'm going to just make a little table here. Count the total number of degrees of freedom, the translational modes, rotational, and vibration. Just really simple calculus, calculation. Right? Let's just see if we can understand this, right? So let's look at HCl first. Right? It's a diatomic molecule. It's got 2 atoms. It's got 6 degrees of total freedom. It has 3 translational degrees of freedom, right? You can move it X, Y, and Z. But HCl only has 2 degrees of rotational freedom. If this is HCl, there's 2 of them. One is this way, and the other one is this way. This is not a real rotation because it's a cylinder, so this doesn't count. So it's only this and this. 2 degrees of rotational freedom for a line. Right. And as you can see, we have 1 mode left, right? 3 plus 2 is 5. There's just 1 left. There's only 1 vibration. And that makes sense because HCl is a diatomic. It only has a stretch. Let's do a different one. Let's do another linear molecule, but this time polyatomic. CO2. 9 degrees of freedom. 3 translational degrees of freedom. 2 rotational degrees of freedom. And what are we left with? There's 4 vibrations. I'll show you those vibrations soon. All right, we'll look at what they look like. Right? We could just keep going down. H2O. Of course, it still has 9 degrees of vibrational free or 9 degrees of freedom because it's got 3 atoms. 3 degrees of translational freedom, but this one has 3 degrees of 3 degrees of rotational freedom. It's no longer linear. It's a 3-dimensional molecule. So for H2O, there's this rotation. There's this one where the hydrogens kind of oscillate around the axis. And then there's this one where it rotates around the plane. There's 3 unique rotations. So H2O has 1 less vibration than carbon dioxide. And the 3 vibrations of water, really, really easy. One is what's called a symmetric stretch, where the H's stretch out like this. There's the asymmetric stretch, where they go like this, they're out of phase. And then there's a bend. Actually, calculating those is very difficult, it turns out. But in some sense, you can kind of get that sense that so symmetric, anti-symmetric, logical choices. But to actually calculate that from scratch is a very difficult process. It's a very high level, graduate level problem. All right, let's do one. Let's do a couple more. In H3, right, this has 12 degrees of freedom, 3 translations, 3 rotations, and 6 vibrations. We'll do one more. CH4, 15 degrees of freedom, 3 translational, 3 rotational, and 9. Yeah, it's pretty easy to convince yourself of that. If you just want to take a couple objects at home, and convince yourself that might not be hard to find an object that looks like water, or a hammer is a really good option. A hammer looks kind of like water where we go with D and H here. It makes it symmetric, and it's very easy to see in the hammer that you have 3 degrees of rotation. Pretty easy. We'll come back to the rotational thing. Actually, next week we'll talk about rotation. Hold on to that. Hopefully I'll bring in a hammer. Actually, maybe do I have one? Do I have something like a hammer? No, I don't. I'll bring in a hammer next week for that. Hammer's a really, really good object to describe rotations, actually. Okay. So I want to just show you. So again, this is just pure qualitative analysis, right? We don't really know what the energy levels look like. We don't know if they look completely like we say methane has 9 vibrations, but how does each vibration work? What do they look like? Are they intense or not? Are their transitions dark? Are they bright? You know, there's a lot of different questions we have to ask. All right, so we have to just make sure that the theory, where the theory leads us, the quantum mechanics leads us to what happens. Right, to figure out how does the theory of this vibrational system, we have many, many vibrations, how do they all kind of simplify out? What does the math simplify to? So spare me just a few minutes of mathematics here. We're not going to do too much, but let me just convince you that what happens is that this system, essentially these 3 and -6 vibrations, each one of them, what we're going to see is that each one of them acts like a diatomic. Right? They have the same exact properties as the diatomic vibration. It's just that they represent these collective motions of the atoms. And so there are many atoms moving, but in terms of their physics, in terms of their spectroscopy, it's like you have 3 and -6 diatomics built into your system. All right, so let's look at that. All right, so remember that the way that we defined and solved the basic harmonic oscillators, we defined the potential energy. Okay, so let's do that now for this very, very complicated system of 3 and -6 coordinates. Right, so in a complicated molecule, we have 3n minus 6 vibrational coordinates. Right, and let's just call them, right? We'll call them, there are a set of coordinates, we'll call them x1, x2, maybe I'll give them little vectors, x3 to x3n minus 6. So these are these collective motions of the molecule. So here's an example. H2O. Coordinate x1. Looks like this. It's the oxygen moving in this direction. And the hydrogen's moving in this direction. So it's this collective motion. There's a center of mass in the molecule. Here's the center of mass. So the idea is that the hydrogen stretch and the oxygen has to pucker in the opposite direction. So the center of mass never changes. All of these, the center of mass is fixed. This is x1, x2 is something that looks more like this, where this atom is stretching out. And then the other oxygen, hydrogen is going in. And then in order to compensate for that, the oxygen is moving in this direction. The center of mass is still in the same place, right? So this first one's called the symmetric stretch. And this is called the asymmetric stretch, or the, sorry, it's called the anti-symmetric. Is it asymmetric? I think it's asymmetric. And then the final one is the bend, which is water's most important, one of water's most important motions, which is where these two hydrogen atoms bend in like this. And this hydrogen oxygen pumps up a little bit. This is called the bend, or the libration. Libration is another word that chemists like. All right, so these are these collective motions, right? All of the atoms are moving collectively in some trajectory. So think of these coordinates, these x's are actually vectors of all the coordinates of all the atoms, but all of the atoms, all of the coordinates are moving along a certain trajectory. They're all moving in a certain way. And these are the three different unique ways for the water molecule to move in those ways. Three different collective coordinates. All right, so you can imagine that each one of these collective motions has a potential energy. The potential energy of the molecule changes as I move along x1, x2, or x3. All right, so we can define a potential energy surface. Find a potential energy function. Right? And it's a V, right? And it's a function of all the coordinates, all the collective coordinates. Okay, and you can imagine, right? You can imagine, just like we have for the diatomic, right? That the diatomic has one collective coordinate, which is just the stretch, right? Stretching. There was this equilibrium position, right? The equilibrium bond length, where the spring length just relax, right? So every single one of these, in some sense, also has equilibrium position. Right? Just water normally, just floating out in space by itself, no energy, right? X1, X2, and X3 are all in their equilibrium spots. The molecules are equilibrated. So each one has an equilibrium position. And we're going to write the potential in a polynomial way. So we're first going to have a zeroth order term, which is the potential evaluated at the equilibrium positions. I'll just call them x1e, x2e, These are the equilibrium positions. Right, so this is the energy of the molecule at rest, basically, potential energy at rest. And then we're going to have a linear term, right? We have a constant term. It's a polynomial expansion, a Taylor series. We're going to use a Taylor series here. Right, so we start with a constant term, and then we have a linear term, then a quadratic term. So the linear term is a sum from I equals 1 to 3n minus 6 of the derivatives of the potential with respect to the coordinates evaluated at the equilibrium position times the displacement from equilibrium. Right, so that's our, we have some slopes here, right? This is how fast the potential changes as you move along the coordinate. That's a slope times a linear function of x. And then finally, we'll just go to the second order, where we have second derivatives. But we're going to have two sums because we have to sum over all the different components. So we have the second derivative of the potential, which is the curvature of the potential, as we move along two of the coordinates. Right, so how does the potential change, second derivative of the potential change, as I move along, say, x3, x2, or if I just move along x3, that would be the second derivative of the potential with respect to just x3. Right, so just calculating all the potential terms. You guys remember from Calc 3, I don't know if these terms ever were given out. This is what's called the Jacobian. They're all the first derivatives of your function. This is what's called the Hessian, which is the second derivatives of your function with respect to all the coordinates. Those are some math terms for you. And then, of course, this is multiplied by a term that's proportional to the displacement along these coordinates squared. And there's a factor of 1/2 on the side. I forgot to add. Okay, so a lot of math, but we can simplify this very, very quickly. All right, what we're going to assume is that the potential at equilibrium is 0. Right? It's just some number. Okay? So we can just pretend it's 0. We can set the energy so that this is 0. Right? Just set energy scale. So equilibrium is at 0 energy. Right, so displacements are going to be a positive energy change relative to the minimum, which is 0. Remember at equilibrium, right? So the next term is the slope of the potential at the equilibrium point. Well, that's the bottom of the potential, the minimum. So this derivative is always 0. Right, we're at the minimum. Right, we've evaluated at the minimum, at equilibrium, which means that the function v is minimum, right? Which means that the first derivative is 0. Okay, so that term goes away. Great. So we're just left with this really, really complicated function here, which is proportional to the second derivatives. So we're going to call this term right here Fij, which is called the force constant between I and j coordinates. Remember that the second derivative, we're at a minimum. So the second derivative is a positive number. This is just a number, and it's a positive number. Right? This has to be greater than 0 by definition, because we're at the minimum. Right? By the second derivative rule, it has to be a positive value. All right, so our potential is defined by these force constants, which are a second derivative with respect to these motions. All right, we've got a lot of them. And how many of these force constants do we have? Well, theoretically, we have 3n minus 6 times 3n minus 6. There's 3n minus 6 squared of them. Let me go ahead and let me just go ahead and copy this over. Our net potential now is this thing. So this is our potential. And these are our force constants, Fij. There are 3n minus 6 squared of them. All right, well, that's a really scary number. Right? When we get to methane has 9 atoms, 9 vibrations, right? So there are 9 unique coordinates, which means in order to define the problem this way, we need 9 squared, 81 different numbers to define the vibrations of methane. That's a real problem, right? What this is telling me is screaming for me to do something about this to reduce that number. Methane requires 81. That's miserable. Who the hell wants to measure 81 different things? Okay. It's a linear equation of 81 variables. Terrible. We can take some trick. There's some tricks though. So what I'm going to do instead is I'm going to define a matrix F. Right? And it's going to be this big matrix that has 3n minus 6 columns and 3n minus 6 rows. Okay. And in that, I'm going to put each one of my Fij's. Right. So I'm going to have a bunch of force constants in here. I'm just going to tabulate in Excel all of my numbers. All right. So I've got F11 here. Down here in the bottom right, I have F3n minus 6, 3n minus 6. Over here in this corner, I have F1, 3n minus 6. There's F22, F33, so on and so forth, right? There's lots of different ones. Oh, sorry, I did this wrong. All right, this is, no, that's right, that's right. F1, 3n minus 6. This is F12, F13. This is F21, F23. Right, I could just fill in this big Excel spreadsheet of all my force constants. Right? There's some features that I can find. What are some properties of this? There are 2 important properties. First of all, one is that all of them are positive. There are no negative numbers in this big matrix of numbers. All positive numbers, right? Because everything's at a minimum. The second derivatives are all positive. There's one other property. F12 is equal to F21. This is a property of second derivatives. When you have a second derivative of a multivariable function, that's a derivative of 2 different variables. Say this is f of x and v of x and y. The second derivative of v with respect to x and y is the same as the derivative of y and x. I can just flip the indices. They're symmetric. This is probably something you learned in Calc 3. Second derivatives are symmetric. So Fij is equal to Fji. Okay, so I don't actually have 81 numbers. Right? In some sense, everything above this diagonal is the same and mirrored on the other side. And so if I draw a big kind of diagonal line through here, right, everything on the right side is mirrored on the left side, right? It's a symmetric, a positive symmetric matrix. Mirrored around the diagonal. There are 3n minus 6 unique values here. And then there's all this junk on the side that's mirrored twice over. So it's double counted. We can figure out how many unique numbers there are. It's not that hard to do. But there's a property of matrices that are positive, symmetric, and square. That's another important thing. It's a square matrix. Now we can always multiply this matrix by a special matrix. We can always change our coordinates. We can redefine what x1, x2, x3, all the way to x3 minus 6 are. We can change them so that this matrix is only diagonal. Zeros everywhere except for the middle. We can always take this matrix and represent it in a different form where the matrix is purely diagonal. There's only 3n minus 6 components. So what we're going to do these types of matrices always have an equivalent form that is only has diagonal values. Right? So the process of calculating this is a pain in the butt, but the computer can do it. So the idea is that we have this matrix here, right? And these entries correspond to our collective coordinates. These are, in some sense, the labels. These are the labels of our matrix, of our Excel spreadsheet, columns and rows. I can create a new set of coordinates. Right? This transformation always exists. So I'm going to write always possible. To define new coordinates where this matrix F just has values on the diagonal. These are some new collective coordinates of all of our atoms. All right, so it's some other different motion of atoms. They're all collective, but they're collective in such a way, right? What does this mean? This means that the only thing that one motion depends on is itself. Right? Remember that these force constants tell you how does one coordinate change as you change another. That's what these off-diagonal elements are. It says these force constants tell you how does the second coordinate change as you stretch the third coordinate. Right? And then here in this situation, all we have are how does the first coordinate change as we move the first coordinate? How does the second coordinate change as the second coordinate moves? And all the other ones are 0, right? So these are all independent motions. So these are 3n minus 6 independent motions. I'll just write here just as a note. How does the stiffness of x2 change as I vary x3? Right? Remember, that's not what we want. We don't want everything to be dependent on each other. So we're going to choose, and it's always possible for us to choose a set of coordinates where there are no dependencies on all the different coordinates. Right? They're all independent. One does not affect the other. So these are some new coordinates, x1 prime, x2 prime, all the way down to x3n minus 6 prime. These new coordinates, which are the x prime sub I, are the 3n minus 6 independent vibrations and they're called normal modes. The conclusion is that every molecule has a unique set of 3n minus 6 or 3n minus 5 independent, uncoupled normal modes. Each one is a unique vibration that has a unique force constant. All right, so how does the quantum mechanics work out now? Very simple. The potential now for our function is now a sum from I equals 1 to 3n minus 6 of the second derivative of the potential with respect to these special coordinates. Right? Remember, there's no off diagonals anymore. All the off diagonals are 0. So the only ones that survive are the second derivatives along these special coordinates that we evaluate at equilibrium times their displacements. Squared. And I can write this very simply as the sum from I equals 1 to 3n minus 6 of f sub I times x sub I squared. Oh, sorry, I forgot a factor of 1/2. 1/2. All right, so our Hamiltonian for vibration looks like a sum 3n minus 6 I equals 1 of the kinetic energies of each of these motions that have a reduced mass times the second derivative with respect to their displacements plus v of x, which is the sum from I equals 1 to 3n minus 6 minus h bar squared over 2 mu, second derivative, plus 1/2 f sub I x sub I squared. This should look a lot like a harmonic oscillator, right? We have minus h bar squared over 2 times the mass times the second derivative, right? This is the kinetic energy, plus 1/2 some number, k, x squared. Right? This looks a lot like harmonic oscillator. So a 1D harmonic oscillator. All right, so what the problem is simplified to is our polyatomic vibration, our energy for our polyatomic vibrations is just a sum
of 3n-6 harmonic oscillators. Everything simplified out.
So F sub I, this force constant, this is K, right? This is what we call K, right? The force, the stiffness. Right? We know how to solve this problem. Right? This just says that the total energy of the system is a sum of each of the modes' energies right? Where E sub I, do a different color, is H bar times omega sub I, V sub I plus 1/2, and K or F sub I, I'm sorry, omega sub I is equal to the square root of K of F sub I, sorry, the force constant, divided by the reduced mass of the mode. And the total wave function is just a product of the wave functions of each mode. It's just a simple product. All right, so a polyatomic molecule vibrationally is just a set of 3n-6 or 5, depending on which one it is, independent, one-dimensional harmonic oscillators. Right? We've just reduced a very, very complicated problem into 3n-6 trivial problems. So any positive definite symmetric matrix is by definition diagonalizing. You can always define a new basis of vectors where that matrix is diagonal. That's something you prove in like linear algebra. Anytime you have a positive definite symmetric matrix that's a square, you can always diagonalize it. In fact, the Hamiltonian itself is also diagonal. Right? It's only dependent on x sub I. This is something that comes up a lot in quantum mechanics. In fact, every operator, it turns out, that we measure in quantum mechanics is square, typically positive definite, and symmetrical. They all can be represented this way. The idea of calculating these normal modes is exactly the same process that you use to calculate the wave functions of a problem if you represent the Hamiltonian as a matrix. Finding the eigenvalues and the eigenvectors of the Hamiltonian, exactly the same linear algebra problem in some sense as calculating these vibration using the same linear. Again, that's why I didn't want to get too much into the math. I just wanted to kind of sketch out the process of doing this. Okay, about 15 minutes. Great. I want to show you something. So let's do an example, right? Let's just see what this looks like. So as I told you guys, this process of calculating these things out for a given molecule is very difficult to do. Right? Even for a triatomic molecule, it's a lot of math. Thankfully, a computer can do it for us. So what I'm going to show you is just an example calculation. Well, anyone who wants to calculate the vibrations of a molecule can just pull up a program and it'll calculate it for them. So what I have here are some really simple molecules. So here I have a definition of a molecule. This is formaldehyde, H2CO. And what I've given the program
are the coordinates in the center of mass frame of each of the atoms. Okay, so these would be X, Y, Z coordinates of each atom, where the origin of this coordinate system is the center of mass. So what I've done is I've defined my 3n dimensional displacement vectors for each of my atoms. I put it in a space, and I told the program to calculate the frequencies. Also asked it to do a couple other things, but we'll come back to that later. Well, let me show you what this looks like. So what this is going to do is it's going to wiggle all of the atoms. Let me just go ahead and open it up again. What it's going to do, it's going to wiggle all of the atoms and try, and this operator means optimize. What that means is it's going to try to find the minimum of the potential. It's going to find that low energy point as a function of all the coordinates where all the atoms like to sit and they're at a minimum. Okay, so it's going to find that minimum, and then it's going to calculate the frequencies exactly using the procedure that I just discussed. Right, it's going to calculate these force constants, these stiffnesses. It's going to make this big matrix. It's going to diagonalize this matrix and calculate the normal values. All right, let's watch it do that. As you're going to see, that is watching it is a different question than understanding it. So I'm just going to start it right now. And here it goes. Be done. The ops contract, we're done now. Okay, all done. So what I've just done is I've taken a guess structure for formaldehyde, jiggled all the atoms and found the most stable position of them, and then calculates the normal modes, force constants. Just go look at the results. And then we'll take a picture of the molecule too. Hope that's not what it's called. I wonder if I need to write this. Sorry. Well, let's do it one more time. All right, just give it a second. Forgot to write it. I need to write it into a file. It's gonna take 15 seconds. Time now. Before you return. Oh. Oh. Let's take a look at this. Zoom a little bit. All right, so this I'm at the bottom of the output file, so it's the end of the calculation. I'm going to scroll because we want to look at the stuff at the end. So I'll just tell you really quickly about these charts. This is it setting up the calculation. It sets up the integrals, all the electrons, and puts everything in orbitals. SCF is solving the Schrodinger equation for the electrons. Property integrals calculating the dipole, the electric field, all sorts of different electrical properties. FCF response is calculating the electric field. Properties, which is the vibrations. Gradient, which is again measuring the energy, trying to find the minimum of the energy. Geometry relaxation, which is jiggling all of the atoms around, trying to find a stable point. You can see all of that took us 14 seconds. Right. This would have taken, if I taught this class during grads 10 years ago, 10, 15 years ago, we would have still been here waiting for it to finish. Really, really fast. Kind of hard to really drive that home. So I'm going to scroll up. There's a bunch of crap here. Let's just go up to the vibrational stuff. Well, let's just look at the properties it calculates. So here are some properties that it calculates. We'll come back to looking at these when we get to molecules a bit more. It gives me the energy of the molecule. This is the energy at that minimum. It's in ridiculous units. These are called Hertz or atomic units. That's an energy scale I haven't taught you yet. That's a crazy one, but it's one that the computer uses. This basically tells you something about how stable the molecule is relative to all the atoms being blown apart. It tells you about the contributions of the energies, and the kinetic energy from the nuclei and electrons. Here's the dipole moment of the molecule. Bye. Calculates the rotational spectra, which we'll talk about next week.
And here's the IR spectrum. Here are the normal modes. So it calculates 11, or sorry, 1, 2, 3, 4, 5, 6. Remember, the H2CO is 4 atoms. 3 n minus 6 is 3 times 4, which is 12 minus 6, which is 6. So here's the 6 modes. These are the frequencies. These are where you would expect to see the absorptions, the fundamentals in your infrared spectrum. These are the intensities for the infrared. You can see that some of them are very weak. U6 is very weak, 4 is very weak, but U1 and U3 are very strong. This is the CH stretch, as we'll see in a second. The stretch is very intense. So it calculates everything that we've calculated before for diatomics, but it does all for these molecules. And each one of these modes just acts like a normal diatomic. We're going to have a different vibrational mode for each one of these motions. Different motion, and each one gives a different absorption. Right? And some are more intense than others. And of course, all have different stiffnesses. Right? This doesn't tell me what they look like, though I can certainly use this information to show you what they look like. But I'll just write them down for you. Just draw them, and then I like to act them out. Another thing that you can get when you know the vibrations, we haven't quite learned this yet, I'm not sure we really will, you can actually calculate entropy of the system, and it gives free energy information. That information comes from the vibrations. So you can do thermochemistry for it, right? Enthalpy, total enthalpy, the total entropy of the molecule. Right? It calculates everything that you would probably want to know about. Okay. So it gave me these 6 modes for formaldehyde. So let's talk about these 6 modes. The first one, we label each mode with a V number. These are its quantum number. Call it nu1, nu2, nu3, all the way to nu6. So the way this is called is the nu1. And they're ordered and decreasing energy. So they're ordered for vibrations are labeled in decreasing energy. It's just convention. So nu1 will be the highest energy mode. That's the symmetric CH stretch. And that looks something like this. We kind of can get a sense, right? The H's point out. And to compensate the C and the O, just place away a little bit. This is at a frequency of 3121 wave numbers. Again, this is high frequency. Remember, the frequency is stiffness divided by the reduced mass. Stiffness might not be that, it might not be that strong of a bond, but these H's are really small. So the reduced mass is really small. So that's why CH stretches tend to be kind of the highest frequency vibrations, is because the reduced mass is small. Mostly just the hydrogen. So the denominator of the force constant, which is compared to mu, is very small. Typically, these are pretty large. Right? That's why, for instance, the OH stretch, like in water, is about 3,600 wave numbers. There's very little, very, very little mass. The next one, nu2, is what's the classic carbonyl stretch. Right? This is a very bright transition. Anyone who's ever done an IR of a carbonyl knows that the carbonyl stretch around 2,000, 1,800 wave numbers is always very, very intense. This one, the oxygen and the carbon move away from each other, and in order to compensate, the hydrogens pucker out just a little bit like this. And this is at 2053 centimeters. Right, so the thing, I can't, this is literally impossible for me to do, right? I gotta somehow have my ass move down and my head move up. It's like really hard to do that. So I'm not gonna do it, but you can imagine what that looks like. not stretchy enough. Nu 3 is what's called the in-plane scissor. Where the hydrogens kind of bend in like this, like scissors. The heads of the scissors kind of extend backwards away from it. Is that 1444 wave numbers? Nu4. This is the in-plane rock. And it's a symmetric form. And this one stretches out. This one kind of comes in. And to compensate for that big stretch, it's kind of going like this. Well, actually, it's like this. This arm is kind of extending out. This one's coming back in. The rest of the thing is kind of rocking this way, right? It's kind of like this. I'm really bad at these. My last TA, I'm not gonna shame Kayla to do these, but her TA did these and was shameless about it, and he was much better than I was at it. There's an anti-symmetric rock. Oh, I forgot to write the energy of this. This is at 1176 wave numbers. This atom kind of goes like this. This one perks up like this. Carbon moves this way, and the oxygen moves this way, right? So you kind of jerking everything around a little bit. Really, really interesting. This has the same energy as the other rock. These actually form what's called a double. These are the same energy by definition, called a doubly degenerate mode. These are very, very common in molecules that have a lot of symmetry. Molecules that are two-fold symmetric like this, right? You see formaldehyde is flat, and you rotate like this and recreate the same structure. It's called two-fold symmetry. Two-fold symmetric molecules always have a doubly degenerate pair of bends, or scissors, or rocks. They're always coupled together. In some sense, there are two solutions to the same equation. Two solutions to the same constraint. Right? They're identical. Kind of like having two zeros of a quadratic function. Right? Two equivalent solutions that take your polynomial 0. Certain molecules that have high symmetry also have these pairs of double zeros, if you will, for certain motions. And finally, the last one, which is my favorite one, so I've studied it. It's the out-of-plane rock. Where the system is jerking forward and backwards out of the plane. So there are, in some sense, these atoms are moving in and out, right? So this is actually what this is the pelvic thrust. That's what this is. U6 is the pelvic thrust of formaldehyde, and it's also the lowest energy vibration by quite a bit. 65 wave. All right, so one thing that's really interesting about this, about these normal modes, is these are the collective motions of the atoms. And when you form, say, for instance, you have a reaction that forms formaldehyde. And let's say, for instance, the way that the formaldehyde forms is through oxygen addition, like they're forming this double bond onto a CH group. Those products in the gas phase tend to be excited when they're initially formed in the CO stretch. And so often you'll see when these simple reactions form these simple molecules, you'll see that the energy from the reaction gets localized
at a certain mode that corresponds to the motion occurring in the reaction. So if the oxygen is being added, very interesting, you'll see in these formaldehyde studies that the CO stretch of the formaldehyde products tend to be more excited than the other ones. Or there's another really cool situation where you can, if you pyrolyze this molecule, which means you just put it under heat, you lose H2 plus CO, carbon monoxide plus H2, which just breaks apart into two simple diatomics. And what you find is that the way that happens is the scissoring motions and the rock motions become extremely vibrationally excited. And this hydrogen right here leaves. It gets plucked off, and then it kind of roams around the molecule and plucks the other one off. So it's not like, it's really interesting. You can show this from the vibrations of the products and the vibrations of the reactants, that the forming, breaking this into H2 and CO doesn't go through a transition state where the two hydrogens come together and bond and then leave the CO, right, like in one concerted step. But what happens instead is one H leaves and roams around and picks the other one off. So it's a two-step reaction. And you can tell that purely by the vibrational distribution of the reactants and the molecule products. You find that this molecule, the formaldehyde molecule, as you excited, gets predominantly excited in the rocks and the scissors. And then the products that form afterwards are highly excited vibrational H2. H2 is forming like this, and the CO is cold and not vibrating at all. So all of the energy gets localized into the H2s, and no energy gets localized into the carbon monoxide, because most of the energy is being transferred through the scissoring in the rock, which affects the hydrogens. H2 forms very excited, but CO forms very cold. It doesn't vibrate at all. So it gives you some sense. The vibrations tell you something about the reactivity, because these are the paths that the atoms follow in order to react. You can kind of think of them as the possible trajectories when they leave the molecule. Okay? So that's really kind of an interesting way to do this reaction analysis. You can learn a lot about reaction geometry by looking at vibrational distributions, because each vibration has a specific atomic characteristic that the other ones don't. So if you have a reaction that prefers one atom over another, see that bias in the vibrational distribution of the reactants and products. Okay, I'm out of time. Have a lovely weekend. We'll start rotations on Monday, and we'll jump into the hydrogen atom within the week.
Yeah. Oh, it should be on your other. That sounds good. Cool. I'll see you. Today's class was low-key intense. It was good though.
Why was it intense?
Was that just me?
Was I intense?
No.